by the name of the god steel pipe aqueduct example. Look to the pictures. We will discover the pipe path the big canal on aqueduct. For example, steel pipe aqueduct is to be constructed to pass the discharge of higher stream A Q equal 1.92 cubic meter per second over a lower stream B at the location of their crossing. The pipe aqueduct is to be supported on two main girders with cross girders every 3 meters. No intermediate support is required. Wood bridge 4 meters wide is required whereas light traffic less than 5 tons could be allowed. Heading up more than 20 centimeters is not allowed. Design the pipe, the hangers, cross girders, main planks, main girders, and bird abutments. Steel pipe aqueduct example. Cross section of higher stream A, cross section of lower stream B. It's located on the plan. This is abutment and the hanger, handrail, main planks, wearing planks, pipes, main girder, cross girder. From equations, we can arrive to stream water area A, then find V at downstream. For steel pipe, flow velocity could be considered 1.5 meter, mean 2 to 3. In this case, we take velocity 1.5 meter per second. The water area of the pipe aqueduct, due to that, we can arrive at Q over V aqueduct. The pipe diameter equal 1.2766. That's not in the nature. For this reason, we take a diameter for one pipe equal 1.3 meter. Here, the actual area will be 1.32732 square meter. The actual velocity due to that will be 1.4465 meter per second. For a check for heading up, we have equations. We have entrance coefficient 0.5, 4 frictions F small l over m, L is about 50 meters, M d over 4, F the corrections there is low for this. We have A and B due to steel pipe. We arrived that EF equal 0.825, and then check for heading up. It's about 24.8 centimeter. The amount of the heading up could be made with limit 20 centimeter by considering two pipes, 1 meter diameter. The actual will be 1.33, hence H will be 17.7 centimeter. The choice of the two pipes solves the problem technically and economically. Okay. Statical design A. Consider section II external loads. In this case, we assume that the crossing work is empty. Very important. The engineer may follow the same steps as in the culvert. In this case, L equal 6 meter, L dash equal 7.5 meter. On weight of earth, we calculated per meter run, 2.7 ton per meter run. The pipe thickness could be assumed initially as 1 centimeter. Internal diameter 1 meter, outer diameter 1.02 meter. On weight of each pipes 1.124 ton per meter run. The total intensity of dead load is approximately 3 ton per meter run, as we show in the graphics. The intensity of the distributed live load in this case, the last we talk about dead load, here about live load. The intensity of the distributed live load on the pipe, we can assume P equal P multiply L over L dash. It's approximately 0.8 ton per meter run. The third I, lateral earth pressures, we assume H equal to, that's clear in the graphics, E equal gamma, the force E, gamma H Ka equal 1.96 ton per meter run. We talk about section II. There is a bending moment and thrusts due to the different cases of loading. This is a vertical load and the horizontal load. Vertical load, we arrive that it's equal W equal 3.8 ton per meter run. And for horizontal, 1.996 ton per meter run. It is in shape, something like that. Positive and negative moment. We arrive that normal force is equal 1.9 ton and M maximum plus or minus 0.2375 ton multiply meter. The intensity of lateral pressure E equal 1.96 ton per meter run. That's horizontal. There is M maximum and the minimum, M maximum positive and negative, 0.115 ton meter. Normal force maximum equal 1.9 ton. That for section II. Complete design for pipe. There is F maximum normal over A plus or minus M maximum over Z. Not more than 1000 kilogram over square centimeter. We have area. We arrive to thickness about, we take it thickness 1 centimeter. T not more than 1 centimeter. Okay, take it 1. Adding 3 millimeter for ratching or rusting. Then T equal 13 millimeter for rusting. This is شكل statical system, something like that, or the bird. For section II, in these cases, there is a W, total weight. We arrive at maximum moment, that's in longitudinal direction. We arrive at moment equal 0.96 ton meter run. F equal M multiply Y over I. We arrive at F equal 9.27 less than 1 1,000 kilogram over square centimeter. That's safe. For this reason, we try to find all P and moment. We design angle, this in direction of transversal direction. Angle, we design it as a section 40-40 multiply 4, choose 2, يبقى 2 angle 40-40 40 multiply 40 multiply 4. We will find that actual and then F actual not less than 1,000 kilogram over square centimeter. That's for angle. For ties, we arrive that D for ties equal 1.35 centimeter. Added 3 millimeter to 5 millimeter for rusting, then phi equal 19 millimeter. For pipe, we arrived that F less than 1,000 kilogram over square centimeter. It's equal 11.66 kilogram over square centimeter. Design of cross girder. Design of cross girder. Assume on weight 0.2 ton per meter. We find the reactions, then find the moment 3.46, Z equals 346 square third centimeter cubic centimeter, يبقى 346 cubic centimeter. Choose brand froge I-beam number 180. Z actual will be 426 then F actual equal 812.258 kilogram over square centimeter. Z actual equal 426 cubic centimeter. For design of mean temper planks, in these cases, in general, we take an available section is to be chosen at first and then checked. The available section is of dimensions 25 multiply 30 square centimeter. We arrived to weight of wearing planks on weight of mean planks. We arrived to M dead load and Q dead load. Then began to work for live load loading. We have 5-ton lorry is considered. Maximum wheel load 1.75. We arrived to I impact 20%. P maximum is P multiply 1.2. It's arrived 2.1 ton. M maximum live load 2.205 ton meter. M dead load and the live load equal 2.319. We arrive to Z and then Z in cubic centimeter. Then choose the section 25 multiply 30 centimeter we had chosen before. Then Z actual 3,750 square meter. It's bigger than Z required. That's okay. For design of mean temper planks, live load, check shear. In this case, we have Q dead load and the Q maximum load. Q small maximum arrived to 4.46 cubic per square centimeter. Choose 25 multiply 30, that's okay. For temper flooring, we use the following sections, something like that. Wearing surface 5 centimeter high and wide 20 centimeter. For sections for mean planks, 25 centimeter and 30 centimeter. Design of mean girder. From the loading arrive from above, we have a reaction. We collected everything for distributed load and concentrated load. There is P dead load and M dead load and Q dead load, respectively. For live load, we put impact 20%. We have reaction R1 and R2. M maximum equal 25.194 ton multiply meter. Then we arrive to reaction RA and RB. RA, take care, and RB. Then we arrive to M live load and impact in these cases, and Q live load and impact. We put M dead load and live load and impact, and Q dead load and live and impact. We have two value for this. After that, in the design, choose French flat I-beam number 1000. ZX have a value and IX have a value. Design sections, and then arrive to F fact less than 1000 kilogram over square centimeter. That's safe. That's broad flange I-beam that appear in this section or in these figures. Check shear. We have everything. We have Q maximum and S maximum, and we try to arrive to Q shear small. We have IX anti-web from tables. We arrive to SX from tables, and then Q shear we arrive at that's 131 kilogram over square centimeter, less than 800 kilogram over square centimeter. That's safe. Design of main girder. Live load, if there is a deflection due to live load only, we arrive to F with W, A, IX, F. Maximum deflection over span less than 1 over 700. That's safety. Design of handrail. Design of handrail. Assume pushing forces of 100 kg per meter round and the spacing between the upright angles 1.25 meter. Force on one angle, it's equal 0.125 ton. We have a moment 0.1 ton multiply m meter, yeah. Z required, we arrive at. Choose seal angle 17 multiply 17 multiply 9. That's for design of handrail. For base plate, length of B of the base plate at the support of the main girder may be calculated as follows. We have this, yeah. This is a law for R. We can arrive at reaction from main girder. It's equal half multiply Fx multiply L small multiply B. We have R, we have I, we have B. B, we can investigate it from the law. Okay, we arrive that B equal 127 centimeter. Base plate dimension 17 multiply 130 centimeter. For abutment design of the buried abutment in the first, we have a reaction 22.16 ton. Area required equal R over F break. Area actual 70 multiply 130. It's bigger than area required. That's safe. H equal 4 meter. Thickness of footing 0.2 H equal 0.8 meter. We arrived to width of abutment equal 1 meter, K 0.2 B, then width of footing B plus 2K, it's equal 1.7, length of footing 4.8, contact pressure on soil, total reaction on abutment that on weight over contact area 1.32 kilogram over square meter. Then and contact pressure on plain concrete, total load on abutment over contact area. It's arrived to 2.267 kilogram over square centimeter. Thank you.